All right, so I couldn't have actually asked for a better keynote right before I start. I'm also actually in the field of computational chemistry. So I'm going to talk today about how we use machine learning methods to accelerate drug discovery. Um, First of all, I kind of want to talk a little bit about how we solve interesting scientific problems. And maybe it's been a minute since you've thought about thermodynamics or anything like that. So interesting scientific problems are a state function, which means necessarily the path between A and B is not always the most obvious thing, and there's a lot of different paths to get there. In science, though, it's not usually the most direct one that we follow, or even a path that ends naturally at the finish we first expected. There's a lot of dead ends, there's a lot of turning around, and there's a lot of crazy things that happen between your start and your finish of a project. That's kind of been a bit of where I've been learning quite a bit between my graduate and then postdoctoral work. I switched from going into quantum mechanics into statistical thermo, and so it's been a learning journey. First, just give a little bit of a framework here for drug development. Hopefully many of you guys are familiar with a bunch of the stages, but this can take more than a decade and more than several $1 million historically. And so then there's been a lot of work primarily in these first two phases to speed this process up. Maybe we can make this funnel even more narrow at the start. So of course, I come in at the early stages. I am the computational chemist. I am the black magic voodoo person trying to narrow this down from potentially a space of billions into hopefully hundreds. So my group focuses on developing approaches that screen a large number of complexes using a common scaffold. So if you're not familiar, my work is in molecular simulations, specifically in an area of molecular simulations that uses lambda dynamics. In lambda dynamics, what we do is we take a common scaffold with a different set of sites of our choice, where we substitute out different molecules. It could be a fluorine to a methyl group. It could be a phenol. It could be a benzene. It's kind of your choice. However, you can't just suddenly go from one to another. So traditionally in lambda dynamics, specifically thinking something like free energy perturbation, you would pick two physical states for lambda, 0 being one substituent and 1 being the other substituent, your two physical end states. However, in these methods, you actually need to sample across the lambdas in order to get actually statistically relevant states. There's been a number of issues of why this is difficult, but my group is now using something called multi-site lambda dynamics, which has addressed some of these issues. And in lambda dynamics, we're able to continuously sample across lambda in a single simulation. Multi-site lambda dynamics does exactly what the name may imply, is that now I can do it on multiple sites, not just a singular site. In fact, here on the right-hand side, I have, this is an indole derivative for HIV reverse transcriptase, which I just recently published. So this, as compared to those traditional methods that I previously stated, is about a 20 to 30 times speed up, which is fantastic. I do not have to individually model every single perturbation. Obviously, that's a large combinatorial space, and I'm not interested in doing that. As well as, of course, no loss of statistical precision. For my project, I came in with the idea that I wanted to create a model that could predict something called a bias coefficient. And so in lambda dynamics, and what I'm interested in, what you may notice is two molecules have distinctly different energies. And in a molecular simulation, gaining access to those energy states may be very difficult. And so what our group does is we then apply a bias to even out the scales, as it were, to explore more of that space. So I had a wish list of 3 Fs going into this project. I wanted my model to be flexible, as in I wanted to be able to do a bunch of different possible substituents, maybe even a large scaffold to a small scaffold. Fast, being able to do this in 1 or 2 steps if possible, and physical, meaning I wanted to use actually the backbone of our molecular simulations to determine the outcome, rather than trying to directly predict a free energy difference, which is what's traditionally used to screen out different drugs. So after probably a year of thinking of different ways to construct and represent my systems, thinking about how multi-site lambda dynamics is actually set up in the back end, I settled on more of a reinforcement learning, or in this case, contextual bandit type format. I wanted it to be flexible, as I just said earlier, and part of that is doing unsupervised learning, allowing it to explore the space potentially even further than what it had been presented during training. So for contextual bandits, you have to provide some sort of context. I'm giving a rough estimate here of a graph, which we do an RGCN, initial representation, and it has some metadata, which I will discuss a little bit later. And then from there, an MLP is actually what is predicting these bias coefficients. We run a simulation, see how we did, and based off of that, we apply or reward or regret, if you're familiar with that sort of language. So there was quite a bit of wandering around for me in the initial journey. And so as with any project, right, problems do arise. Some of those are inherent in the method you choose, whether that be maybe it's in your molecular simulations, or perhaps it's in the type of model you've decided to use. And some of those are things that you finally learn after you run some ML models that are embedded actually in your data set. There's been a number of research papers over the last 5 years that have gone back to some of the large screening papers for drug discovery and noted that there's a lot of actually interdependent structures or a lot of overlap that may not have been obvious at the get-go. And then the last thing is part of this is also following Occam's razor. You may or may not be familiar with this, but it usually says, keep it simple. The simplest solution is usually the right solution. So trying to balance that in your research is very, very difficult. So starting along, I learned very quickly that contextual bandits have a cold start problem. So they may not actually have any idea which direction they should walk either. So a lot of times we use something called behavior cloning, or you've heard it used, the term pre-training in other types of research. And what this allows me to do is say, well, here's vaguely an idea of the type of things you may or may not see. And it gives it a chance to learn the correct behavior I would expect it to perform in order to predict the appropriate biases. Then, if I want to make it a little bit more flexible, there's an option. You know, this is something that you can do embedded in your code, is adding curriculum learning. Maybe I want to start from something as simple as adding a hydrogen. Then I want to move on to a methyl group. Then I want to move on to a benzene. The nice thing about curriculum learning is I can make this more and more complex as I go on. The idea being eventually getting up to adding a lot more to my scaffolds. And then the last thing, of course, is coming back to that physicality. Well, it doesn't always seem so straightforward. If you're not a chemist, maybe this problem isn't so simple, but my initial embedding scheme did not distinguish between ortho, meta, and para. Now, these three are different in energy space, but I was not putting this in energy space when I was first embedding. And so that requires some creative solutions. In my case, I looked at what was available in the research. So there is a molecular force field is what we use that has been done using machine learning. Part of that is they actually used these radial and angular nodes to describe the chemical space around particular molecules. This has already been coded. It was not a bunch of work I had to do. So instead, I moved over from the representation I was using for the substituted benzene that was not capturing this unique chemical behavior into something that's actually a spatial representation. So I'm not collapsing into 2D space or 1D strings, as it were. So kind of bringing that all together, we cannot assume that traditional data pipelines will work perfectly for AI, right? I can't use necessarily always the simplest representation, but I sure as heck want to try. That's why I'm going to be trying to apply Occam's razor, keeping it as simple as possible while still maintaining accuracy and keeping the physics as part of the problem. with that, I want to thank Charlie Brooks. He's my scientific mentor, and Ambuj Tiwari, who is my AI mentor, and he's been a never-ending resource for trying to figure out my path through AI.
So I guess I have a quick question is like, what do you feel is the most challenge part for this work? Is it the like model, the computational power, or the data that needed to?
So the running molecular simulations themselves each take about 2 or 3 minutes for my shortest ones. And so if you need a lot of data, that means you're going to spend a lot of time, in my case, on GPUs, trying to just collect enough information to train the model. So that was hence the reason also unsupervised learning was interesting. But actually representing my chemical space and putting that meaningfully into my model was, for me, the largest and most difficult step to overcome. There's been a lot of iterations of how to represent these things.
If not, then let's thank Paige again.
Hello, it's great to be here. Thank you to the organizers for inviting me. You know, in life, it's always nice to be able to kind of reflect a bit. Like life is so busy, sometimes you just go, 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 and you never really get to think about your journey. So I appreciate that opportunity. So yeah, I'm an associate professor here, been here since 2017 in the chemical engineering department. I want to tell you how I also did a lot of quantum mechanical modeling and still do in my lab, and how we've transitioned more to integrating machine learning. So a little about my lab. So I guess these are the slides that I sent before I updated them. So yeah, a little bit of font changes, but you'll all forgive me. So yeah, we do quantum mechanical modeling and machine learning for energy and environment applications, from synthetic fuel production, a lot of electrocatalysis for water and air pollution remediation, using machine learning to accelerate materials discovery for various applications, including fuel production and like redox flow batteries. So yeah, that's kind of a high level. So you can, so what about my journey? So it's winding. I didn't start with I'm a chemical engineer, fully trained, all the way through from my bachelor's through my PhD. So I started with amorphous materials and touched some optimization algorithms, and then moved a little bit into homogeneous catalysis, organometallics, which we heard about, heterogeneous catalysis from thermal catalysis, so using heat as the driving force. But then in my postdoc, I had the opportunity to go to Berlin, and that's where I got my first introduction to data science and ML, and then the rest is history here. So I was always open to new methods, right? I mean, I felt as a engineer, my strength would never be just trying to develop the next algorithm I can't compete with the computer scientists. I can't compete with the statisticians. I could maybe use their methods in my domain to great effect if I could bridge both fields. That's kind of been my mental framework. And so at the Fritz Haber Institute, I was able to work with Mario Bolli to use an algorithm that he was actively an expert on, something called subgroup discovery, to see could we find local patterns in our data. Instead of finding a global model that just fits all the data, could we find and describe local patterns? And this gives you my first piece of advice. I collaborated with a machine learning expert, and that's a great way to get started on your AI journey. So if you can collaborate with ML experts, that will give you a great head start. So thank you, Mario, for helping launch me on my journey. So around 2015, I was starting to see a lot of signs that AI was going to pick up. It wasn't super pervasive in chemical engineering and catalysis yet. So this is actually a slide from when I interviewed here, and I said, okay, I'm going to study catalysts and materials with DFT modeling, and I'm going to do data analytics. So that was kind of, I haven't fully thought through all the steps yet, but I said I'm going to do some machine learning integrated. I actually never did theme 2, never touched it. So also, when you propose things and you get hired, you don't actually have to do what you say. So this, though, is just some bullet points of things I was thinking of. I felt it was ripe to make an impact in the area, and I still think now is a great time to get involved in AI. It's better than ever. The barriers are lower, the methods are more amazing. It's a fantastic time. So how did I get started? I, wanted to try to hire postdoctoral researchers and graduate students with knowledge in machine learning, especially areas that I don't have. So this helped me move into areas like agentic AI and generative modeling. Collaborating with people is so much fun. So I definitely tried to collaborate with many professors and researchers from around the world, and also industry like Microsoft, to try to learn new things and to launch into new directions. So I encourage that as you're facing challenges in your journey, not try not to do it all on your own. Leveraging resources like Midas and MICDS is really instrumental to me. There's so much there to help you on your journey. Schmidt program has been instrumental, the PODS program. So trying to leverage the resources that are available to you. And I decided to teach a class on machine learning. And that forced me to learn the fundamentals and stay up with modern methods. So if you want to be really good at something, just say you're going to teach a class on it, and then you're going to be held accountable to that. So again, my journey has been really thinking, where could I pick a domain problems where machine learning could make an impact, where I'm not trying to make the most accurate method. I'm not trying to make the next algorithm, because I just don't think I can compete in that space against the Meta and Google, etc. Like they have big teams working on these things. Like where could I make a contribution? So working with colleagues helped me identify some domain areas, like Suyo Linich has been a great colleague in this space. So we worked on hearing about black box models, working with large data sets, deep neural networks, screening materials. I'll tell you a little vignette about that. And then we were thinking, what about interpretable models? Because we want to get physics-based explanations and scientific insight to guide hypothesis formation. So we really spent a lot of time on these interpretable ML models applied to catalysis, and also screening. So here I'll tell you one small story on Bayesian optimization for high-performance iridium molybdenum oxide electrocatalysts for water oxidation. So iridium oxide is a really good catalyst for water splitting to make hydrogen for the renewable hydrogen economy, but it degrades and dissolves in acid. And iridium's really expensive and rare, so you need to reduce the amount of iridium in your catalyst. So we create an initial data set. This has a cold start problem. We do some calculations, train a Gaussian process model, have a measure of the uncertainty, do expected improvement acquisition function to tell us which data points to label next, to explore and exploit, do DFT calculations to fill in data set, and repeat this loop. And doing this with quantum mechanics calculations let us kind of go through the periodic table and map out phases of doped iridium oxide alloys that may be stable in acid. So we were able to kind of see that tantalum, tungsten, and molybdenum doping should be quite promising for iridium oxide. And then we noticed that people hadn't really looked at iridium molybdenum oxide in detail. So in Suyo's group, they made it, tested it. This is showing you the current density versus the applied potential. The more to the left the line is, the more active the catalyst is. So iridium molybdenum is more active than iridium. It's also slightly more stable. So it's more active, it's more stable, and it's cheaper. So that's a win. So we demonstrated this. And this Bayesian optimization for experimental design is a very commonly used approach now that I think is a real workhorse. Something which builds on the foundation models we heard about is here we'd leveraged foundation models that were released to simulate platinum nanoparticles on metal oxide supports. And what we wanted to know is, could we find design rules for supports that would make nanoparticles stable against sintering or Oswald ripening? So in Oswald ripening, small particles shrink and large particles grow, and this causes your catalyst to lose its surface area, its total exposed surface area. So it causes deactivation. So this is like platinum on Syria. And here's a particle migration coalescence where the particles bind too weak to the support. So they just move around and diffuse, and then they agglomerate. So with these machine learned models, we were able to screen many hundreds of supports, predict their stability, use interpretable machine learning to find descriptors that confer their stability, and then we predicted a new support that barium oxide, which was understudied, that actually was improved than like state-of-the-art Syria. So that was a showcase application of how these machine learned simulations let you do molecular dynamics at length and time scales that are previously inaccessible. And then we coupled that with interpretable ML to extract insight. So that's, oh, those are the movies. Yeah, so I'd like to thank some of the people that helped me on my journey and are continuing to. You know, it's a never-ending journey. I thought about that dragon from Never-Ending Story. You know, the journey continues, and we're always growing and adapting. So happy to take any questions.
Hello? Is it working?
I can hear you.
Okay. I was curious, in the molybdenum iridium batteries, about what ratio, like how much of each substance did you use?
Oh, there we were studying 50-50, just because the combinatorics get really high if you try to explore all the stoichiometries.
Wonderful talk. So you mentioned briefly about training on some QM calculations, right? Did you use DFT or wave function or plane wave or what kind of?
Use materials project and then did DFT plus U for the metal oxides.
With the DFT representations that you used, how confident are you that they did a good job representing the metals that you've selected? Because I know DFT has some issues with like transition metals and some other things.
Well, a number of the materials that we predicted to be stable were supported to be stable by literature, and then the one that we made was also promising. So it seemed to do a decent job. I can't promise it was right for everything. We may have missed some phases, but we actually identified some phases that other people missed because they didn't do the full enumerations. But yeah, there's clearly some inaccuracies for some of the materials that may have led to misclassifications.
Not, let's thank Bryan once more.
Can you hear me if it's up here? Perfect. Okay. So thanks everyone for coming out. I'm going to talk about my AI journey, which is looking at AI-driven optimization for decision-relevant power grid operations. So I want to walk you through kind of how we've thought about this problem and how we moved into what our solution ended up being. And I'm going to start a little bit differently. So I'm going to start with an engineering system. And from this engineering system, I'm going to walk us through what we traditionally do when we're designing. And I want you to keep in mind large-scale infrastructure. So when you design it, you build it, it lasts for 50, 100, 150, 200 years, right? So those long time scales. We will think about our users and our use cases, and then we'll take all of this information, combine it into whatever our decision-making system is for that engineering system, and we will have some kind of measurable system performance in terms of how it's performing. How many cars are you moving across your highway? How much congestion are you seeing on the road? What kind of loads can you support on your power system? Now, one of the things that we aren't able to capture when we build something 100, 200 years out is tomorrow's users and use cases, because some of these things, particularly for power systems, have been changing so rapidly in the recent years. And so I want to motivate some of these cases where we're thinking about tomorrow's users and use cases. And I'm going to talk about two main driving factors: emerging large loads. I'm sure you have heard about data centers at least once during this week, if not this week, this past month. In the news, it's talked about quite a bit. And the second being renewable generation, or really any kind of generation being built and sited in a different part of the grid. So to motivate some of the challenges we're seeing, I'm going to start on this emerging large load side. And this is the graph of the Mid-Continent Independent System Operator, which you can tell covers a huge swath of the US, including Michigan. And so I've pointed out where we are here on this map. Within MISO's footprint alone, by 2027, it's estimated that there's going to be a 130% increase in data center loads. And this is just data centers. It's not considering electrification of any other resource. It's not considering our transition. It's not considering anything related to onshoring of manufacturing or any of these other things that might impact our system. The second element that I want to talk about, I have a map of Texas. It could be a lot of other places, but Texas is a really good example of this because they have the wind panhandle. And basically, you have a lot of generation come onto a part of your system that you didn't design your system for, but all of your loads are located very far away along the coast. So now you have to move all of that generation over to your loads. And so in both of these cases, what you end up with is a grid infrastructure that was not designed for the use cases that we see emerging and for use cases that are going to persist for quite a long time. And in both of these cases, the challenge that we see is congestion. So congestion basically limits our ability to move power around. And what I have here on this animation is a map, once again, of MISO. And the colors you're seeing are representing what we call our locational marginal prices. This is the wholesale price of electricity. If you see deep oranges and deep reds, those are really high prices, and those are typically where we have a lot of load. If you're seeing deep purples and blues, those are actually can be negative prices or very low prices, and that's because we have too much generation. So if you could imagine that you have more wind generation than you can push out to a load center, where you have that wind generation, the price becomes negative. It's not good for the market. And your load center, the price becomes really high. That's not good for your consumers. And so congestion is becoming more challenging because of variable conditions, changing load patterns, changing generation patterns, and I haven't talked about weather, but I promise it's part of the story as well. So what do you do when you have this kind of challenge with this emerging changes in our infrastructure and where we see more congestion on our grid? And my group has been exploring the use of flexibility in existing transmission infrastructure. So rather than thinking about, can we just build the grid brand new, which is frankly not possible, that requires us to rebuild the airplane while it's in flight, is the analogy we like to use in our field. My question is, can we use flexibility already there? And so with our transmission infrastructure, we can do something called network reconfiguration. It's basically, imagine you have a highway and you can choose to move one of the highway lanes to another location, open a bridge, reconfigure it. It's almost like the Hogwarts staircases that shift and change, right? So imagine that, but on our power system. And if we can do that, we can do a couple of different things that allow us to improve our congestion on the grid. So here I have our base topology. Let's see. Okay, so here we have our base topology. So suppose we have this really simple system, and they're all connected. One action we can do is we can basically just open a transmission line. It sounds counterintuitive, but that can actually sometimes really help because of the way physics is coupled on these two substations, and opening that line can actually give us more flexibility and the ability to push more power on the two remaining lines. The other action that we can do is what we call bus splitting, where we basically take this one substation, and it physically doesn't change from the outside, but electrically we decouple it into two independent substations. So now what we have is we have this graph from a 3-node graph to what has now become this 4-node graph, and that is where our bus splitting action happened. So our question is then, how do we solve this problem and how do we frame it? So we typically will take all of our system models, our system characteristics, this includes our generating sources, our loads, network constraints, including our flow limits. We'll model this as a mixed integer optimization problem. We'll send it to an optimization solver, and we ask that it finds our optimal network topology that maximizes this power transfer. And our decision is basically which switches are we turning on or off, right? So we have this binary decision that we're making. And if we do this, we've run some test cases. My PhD student, has run some test cases on an IEEE 30-bus system. And so these are some results. There's a bunch of numbers. You don't have to worry specifically about the numbers you see. But in this row, it's showing you where you see the dash. That system isn't actually feasible. So we can't satisfy the load on that system. The base topology can't support higher loads, for example, data centers in MISO, but reconfiguration can. And if we add bus splitting, it further extends our flexible operating region because we have more flexibility in our system, and then we can support even higher levels of load without having to build new transmission infrastructure. So I'm showing you these results on an IEEE 30-bus test system, and these are pretty standard in our community. But this is the reality of the US grid, right? So the US grid has 642,000 miles of transmission. That's almost 30 times around the entire Earth. And the model that we have of an open source synthetic model we have of the US grid has 82,000 buses. So how do we go from 30 to 82,000? And our group has been investigating scaling this problem using different AI methods. And the one that we've really been focusing on is using neural networks, and specifically using neural networks to approximate our optimization solvers. So the inputs remain the same, the output ideally remains the same, and all we're changing is the decision-making module and what's running our computational decision-making. So in a very short amount of time, to get across the idea of where the challenge of this comes from, imagine that we are predicting solar generation from a particular plant tomorrow, right? This is a very simplistic example, but we're gonna take in historical data. It's gonna give us some 24-hour profile of how much we expect to see from that solar farm. And this little blip over here is basically our statistical model is saying that because there's some error in the data or there's some kind of numerical funniness happening because in this really nonlinear function, we are generating at nighttime, right? And that defies the laws of our physics. We know that there are ways to address this in all of our examples, but really the challenge is how do we embed physics, example, but in our large infrastructure optimization problem to enable AI applications for safety critical engineering systems like our power grid. And the added challenge is that we have these switches that have to be on or off. They can't be in, halfway open, halfway closed. So within this, we've been going through a couple of different ways where we can embed the physics, and this is the majority of our AI journey. So how do we think about the different physics of our system? How do we embed them into our decision framework in different ways? And how do we do so in a way where our results are scalable? They can be tested with limited amounts of data because data is limited, and we can show that we can get good performance results. So I'm not going to talk about these in detail, but I want to give you a sense of the flavor of techniques we've been using. The first is to exploit operational requirements of power grids. Sometimes operators will make certain decisions that we might not capture in our physics, but they are because of protections, regulation, market design. And all of these things are things that we can capture if we collaborate with industry. For example, Siemens and RTE, which is the French system operator, have been collaborators with us on our projects. The second thing we can do is try to repair our decisions, right? So our neural network may predict something that isn't actually physically realizable. How do we take that solution and move it towards something that is physically realizable? Can we use power flow proxies? Power flows being the actual algorithms and physics of our system that we are aware of. Can we do some kind of combined unsupervised, supervised training framework? So offloading some computation to a supervised module and then doing an unsupervised module with that in line and a repair layer. We've tested some of these different frameworks. And then the last, coming back to this idea that any of our large-scale infrastructure is underneath a network or a graph. So how can we leverage GNNs, gated message passing, and type-aware edges to actually encode more information about our physical system that we know into our training pipeline? And across all three of these, we can also use some standard tricks that are typical in this field for developing what we call AI-based optimization proxies. We've used different versions of each of these three techniques in different combinations across different applications for distribution and transmission grids. And what I want to focus on is just that last kind of showing you that we are on our way there. We have something that works for transmission reconfiguration and looking at that bus splitting problem. That very bottom row is an instance that was not previously available with Gurobi, which is a commercial, probably the best commercial mixed integer optimization solver on the market. And we were able to solve this data from a heuristic optimization proxy. And so we do get these significant speedups in computational time and potentially the ability to solve problems that could not be solved for grid scale operations. And so just our last slide. Obviously, this isn't work that I've done on my own. This is work that's been done as part of a team. And so I've highlighted some of the students who have been instrumental in different aspects of this work over the years, as well as multiple different academic collaborators and industry collaborators that have taken part in this project. And will continue to do so as we keep pushing the boundary of what this topic has to offer. Thank you all, and I'm happy to take questions.
Yep. And do we have any questions? Oh, please.
I can hear you.
Okay, great. Thank you for your presentation. Have you reached out or gotten any feedback from MISO or ERCOT in Texas or the local utilities here in Michigan or the Midwest? And what has their feedback been if you have reached out?
Yeah, so I can break this up into two parts, distribution and transmission systems. They operate differently. So we've talked to a distribution utility in the Pacific Northwest, and we shared with them our results, and they were really interested in it. But there are still some actual engineering challenges in deploying this in the field and in deploying it quickly for distribution systems. Some of those are less related to actually deciding what their best topology would be, and more so about how do we ensure that our existing protection schemes, for example, can work under those different topologies. They were interested in this as a technology and would have actually wanted to deploy it if not for that challenge. And it's something they're still thinking about in terms of what to do and how to move this to field. In terms of chatting with our transmission system operator, so MISO would be an example, we actually are having conversations with them trying to understand how we can make better decisions, but also their interest is also how do you create the parallel market structure. And without going too deep into electricity market design, once you start changing the topology, the way that our US electricity market is designed is it's dependent on the topology. So we have what we call nodal prices. And if you start taking a node and splitting it into two, what happens to those prices and how do we think about some of those challenges are another piece of the puzzle of the question. So we are chatting with them to see if there are opportunities to kind of move these things forward collaboratively.
And then just, if I may follow up, as an energy lawyer myself, and just to think about the grid, which is regionalized, if you will, into ISOs or ITOs. Have you thought about maybe partnering with a law school and thinking about what it might mean to have a truly national strategy around energy transmission networks, given that there are regional bottlenecks, and what that might do for a singular energy strategy across the U.S.?
I have not, but we should, and I would love to chat if you would like to chat a little bit more. We should touch base. I think there's a lot that I could learn in terms of that, and I think there's also a room to play for planning and operations to then go hand in hand as well. This is very much an operational question, but obviously planning and where do you build out HVDC lines between Eastern Western Interconnector with ERCOT or whatever comes in. So I think there's a lot of movement that we could have in aligning planning and operations as well.
Because the areas are not permeable, energy bottlenecks, and why you'll get price spikes in one region where you don't get in another. And
Yes.
it seems like an artificial construct so that you could solve the physics issues with the modeling of the grid across the nation. That would be super cool.
You would fix the pricing issues. And if I may take another 30 seconds, there was a really interesting instance, you might already know about it, last year in May when MISO asked Entergy to load shed about 100,000 customers. And if you look at the price map, I don't have it on this one, but if you look at the price map, it was deep red down here, and then you saw the small connection to MISO South, and there was a bottleneck. There were other issues as well, but if you imagine you had more. So when that generating facility failed in Entergy's footprint, you could put more power down. And that might be an operations issue, it might be a planning issue, but thinking about what this means for regional bottlenecks would be really critical.
So you can see how all of your work feeds into what could be.
Mm-hmm. Thank you.
Thank you. And I guess we have a question from the Pigeonhole. Can this be applied to constraint-driven manufacturing to reconfigure the plant lines?
I haven't thought about that. It sounds interesting. I have thought about other similar infrastructure networks like gas networks or road and transportation because they follow similar parallels and physics flows. That is an interesting conversation to be had. I think it might depend on the additional constraints that we would see on the system. But I think that some of the learnings that we've had in terms of what works, what doesn't work, and where bottlenecks are might be helpful. So wherever that question came from in the room, if you want to chat and reach out, I'd be happy to share what some of our challenges have been as well. And maybe there are places where our findings could be helpful for your application too.
Thank you. And yeah, let's thank Rabab again.
Good afternoon, everyone. My name is Vijay Giri, and I'm a PhD scholar at University of Michigan, Dearborn. And what I'm presenting today is a small but independent project. It grew out of something, the conversation that we had with the local smallholder farmer. And Honestly, when we began this project, we didn't realize that it was something worth presenting, but when we worked through the problem, it became something that genuinely interested us. So we have this two world of agriculture. So most of the agriculture decision support and forecasting system, they are concentrated for the row crops, and honestly for a good reason, because they have months of predictable biology and a year-round market. But this reality is completely different for specialty crop growers. I mean, so they are not operating in months. The biology is compressed, and Monday the spears emerge. Wednesday it's a big harvest, and by Saturday it's a literally waste. So most of the crops that falls under this category have a window of harvest that's even less than 48 hours, and the shelf life post-harvest is another 3 to 7 days. So it isn't just the asparagus or any, so asparagus was our MVP actually, so that's why I'm going to focus more on it, but it's not even that crop, it's actually most of the crops in that sector. So the biology is just unforgiving and the economics follow. And this is clearly not a niche problem actually. So even though the specialty crop occupy less than 5% of the US cropland, so they contribute significantly. That would be nearly 1/3 of the total crop value. So what does the morning decision actually look like? So these are the three questions that every morning a Michigan asparagus farmer has to juggle through. Do I mobilize harvest crews today? Because we have to absolutely lock in those S2A labor contracts days in advance, and you just cannot call them in the very last moment. And do I hold everything? Do I ship everything that I have right now, or do I hold for better price tomorrow with a shelf life of just 3 to 7 days? That is not an option, or a very high risk option. And the third and the big one would be a massive import surge from Mexico. So we're talking 10 million pounds per week. So the market, it's very possible that the market might collapse even before the farmer has picked up a single spear. So actually we we navigated what the existing ecosystem, the support system is for the farmers. So we have this cooperative, the MACMA, that negotiates the price floor for the processed asparagus, not the high value fresh ones. And we have this Michigan Asparagus Advisory Board that, that specializes in marketing and production research, and 100 plus independent farms picking, packing, shipping fresh markets. So these were the gaps we got ourselves into. And so we visited the official resource, the data for decision page and what they offer the growers today. So processed volume, fresh shipments, it hasn't been updated since 2022. The import source tracking ends in 2021, and the cost of production, so nearly a decade old. So basically, the farmers are being asked to make a decision that changes by the hour using the data that is worth the years old, and even in some cases decades old. So what does that lead to? So it's clearly visible with the data, and it's pretty stark. So in just 1 year, nearly 1/3 of the total US asparagus value collapsed. And in 2023 alone in Michigan, nearly 650,000 pounds of asparagus was harvested but never sold, because, and it's not because that the crop failed, actually the crop did really well, but because the market wasn't there when it entered the market. And so the break-even economics of the domestic production simply couldn't match the the import pressure, not without better tool or better market intelligence. And so we have this stat right here. So this is how bad it got in California, which used to be a major producer of the asparagus. So USDA stopped completely reporting on it after 2024. So at this moment, it no longer becomes a forecasting problem, it is a survival problem. So the tools we are building actually, we wouldn't claim that it could reverse the action, but we are giving our best hope to the farmers to give a better fighting chance. And so what is really causing this crisis? So this is like a classic David versus Goliath situation right here. So on the one side, we have these huge corporate farms who have all the fancy tech you can think of, IoT sensors, satellite imagery, everything you can think of. And on the other side, we have these 1.8 million small and mid-sized farms. So what do they have? They have the weekly PDFs, the fragmented historical data, and most of them have the intuition. So, and recently the USDA also offered a 100K specialty crop grant to the MAB, but that basically went for the soil and plant health, not for the forecasting or any sort of decision support. And so why do we need, so what is the wrong with the existing forecasting models in the first place? So actually it's not the raw accuracy that we are interested in. Even the simple time series models like Sarima or Rima can do better in this job, but it's actually being able to represent the actual structure of the problem here, because a simple historical mean or data is not able to predict that market shift that's coming. You need all kind of high dimensional market signals in order to incorporate that. And another thing is that the yield and price are negatively correlated. So any tool that basically forecasts that the harvest will be great and doesn't also predict that the market price is about to crash, then it will lead the farmers to make exactly the wrong decision. So we have to absolutely jointly forecast them. So this is the entire system, but I'm not going to talk about this. So this is the more user-friendly version of it. So we have a public data, all the market signals. This is clearly the most difficult part, getting this right, because they are fragmented and they do not talk very well to each other. And at the core lies the AI engine. So it's a model zoo of several deep learning, including even the attention-based architectures that jointly forecast do the probabilistic forecast of the yield and price together. And then we use the Gaussian copula to preserve that yield price relationship, and out comes the harvest decision in the form that it maximizes the profit and minimizes the probability of loss using several thousands of joint cases, Monte Carlo optimized joint cases. So that is basically all of it. So just 2 people, no lab, no funding. So, and and one of them is also not even from here. So,
Thank you, Vijay. And do we have any questions for Vijay? Yes, please.
actually, I wasn't done with the presentation, but I was going to get there. Yeah.
So sorry.
It's okay.
That's never happened.
Yeah. So actually, I was going to talk the most challenging. So this was the most challenging task that we had to do. It took even more than building the model and training itself. So we had these heterogeneous sources. They had different reporting formats, a different frequency of how the data is updated, and getting them all into one unified pipeline and synchronize them independently. That was the most challenging part. So we had to waste most of the time in it. And another challenge was, so we originally thought that there would be a clear winner, best model. We were going to be selecting that, but there was not. If you look at the heat maps at the right, so across the forecast horizon, across the target and region, so it continuously flips. So our solution was, along with this model zoo, we integrated a performance-weighted ensemble model as a safety layer. And one of the thing that I want to be transparent about is that even though the uncertainty prediction for the yield was calibrated well, but it wasn't well for the price. But actually, it doesn't matter much because since we are jointly forecasting them and we have a well calibrated yield as an anchor, so the question is no longer what the price will be tomorrow. So given the full distribution of price and a well-calibrated yield model, so what would be the maximum profit or the minimum probability of the loss? So that would be the question here. So we also had to look at, prove that our model learned the real market and not the market noise. So for these, the temporal fusion transformers, so they comes with the interpretability. So this was the feature importance plot. And so what does that decision actually look like? So I wouldn't care much about the benchmarking with the baseline model. So the most important data here is that for Michigan, so it's a 2.6x improvement in expected profit, and the probability of loss decreases from 44% to 1%. So basically, this model can turn a high-stakes gamble into sustainable business model for those small specialty crop growers. So we were operating completely on their gut feeling. So that is our contribution. So what would we like to say? So we even didn't decide the model before starting. So we began with the decision. We had a real problem. We had the constraint of infrastructure. We had nothing when we started. So model came second. And sometimes the constraint becomes the innovation. And the domain knowledge is actually not the soft skill. Actually, you need to know the industry inside out. That's absolutely load bearing. And my final suggestion would be, so build for who has nothing, not for one who already has everything. So that is my time. Thank you.
Thank you, everyone. So the question is, did you thought about using the agentic coding tools like Cloud Code or dedicated skills to automate the data fetching and cleaning pipeline?
So honestly, I haven't thought about that. I would like to appreciate about that suggestion. This is a work in progress, so we have already submitted one paper related to it. So we still have 2 out of 3 of those questions. So this is just phase 1, and thank you for the suggestion. Appreciate it.
Thank you, Vijay.